All right, let's jump right in. Inside every single object around you, yeah, the chair you're on, the phone in your hand, the building you're in, there's this incredible invisible world. It's a complex dance of pushes and pulls happening constantly. Today, we're going to decode the blueprint of these forces. We're going to understand how things bend, how they deform, and ultimately, how they break. So here's the big question, right? For any engineer, this is it. How in the world do you find that one critical spot, that one specific angle inside a complex part where it's most likely to fail? Nailing this is the key to designing everything safely, from jet engines to skyscrapers. And trust me, the answer is way cooler and less obvious than you might think. To find that one weak point, we have to zoom in. I mean, way, way in. We're about to go on a journey deep inside the material itself to check out the forces that are battling it out on a microscopic level. To get a handle on the whole structure, we've got to start small. So imagine we can just pluck a single infinitesimally small cube of material right out of the heart of a steel beam. The forces acting on this tiny cube's faces, all the pushes, the pulls, the sliding forces, they're a perfect snapshot of what the entire structure is feeling in that one spot. This little guy, this is our starting point. Okay, so you can imagine the forces on our little cube are, well, chaotic. They're going in every direction. So how do we bring order to that chaos? Well, we need a map. Let's see how we make one. And this is our map. It's called the stress tensor, and it is an absolutely brilliant tool for organizing all that chaos. It takes all 9 of those force components acting on our cube. You got 3 direct pushes and pulls, and 6 of these sideways, sliding, or shear forces, and it arranges them perfectly into this neat 3x3 grid. Don't just think of it as a bunch of numbers. Think of it as a complete fingerprint of stress at that one exact point. So, what this really means is that we now have a full mathematical description of every single one of those internal forces. We've captured the entire 3D reality in one elegant tool. But, a map is only useful if you know how to read it, right? Our next job is to find the most important information that's hidden inside that matrix. And that leads us to the next really cool stage of our quest. We're going on a search for purity. We want to find a much simpler, much clearer way to look at this whole complex stress state just by finding a special perspective. So here's the goal. Imagine we can take that tiny cube and just rotate it in any direction we want in 3D space. What we're searching for is a kind of magical orientation, a special angle where all of those complicated, messy shear forces, those sliding ones, completely vanish. They just go to zero, leaving only pure push or pull. Pure tension or compression. These magical angles, they're called the principal planes. And believe me, the stakes couldn't be higher. This is not just a math game we're playing. This quote here really gets to the heart of it. For a structure to be stable, everything has to be in perfect equilibrium. If these forces don't perfectly balance out and sum to zero, it means the material is failing at an atomic level. It is literally tearing itself apart. So, how do we find that pure orientation? We use this incredibly powerful tool, the characteristic equation. Think of it like a mathematical machine. We feed our messy stress tensor into one side, and this machine is specifically engineered to solve for the one orientation where all those sliding shear forces just cancel each other out and disappear. And when we solve it, boom, out pop 3 answers. These are our principal stresses. You'll often see them called sigma 1, sigma 2, and sigma 3. They are the absolute maximum and minimum push-pull stresses in the material. This is the pure truth of the forces acting at that point, with all the confusing shear noise completely filtered out. Okay, so we found this state of purity, but now let's look at something even more fundamental. Something about the stress state that is absolutely 100% constant no matter how you look at it. These are the stress invariants, and honestly, they represent a pretty profound idea. Even though the individual stress numbers seem to change as we rotate our little cube, these 3 special values, we call them I1, I2, and I3, they never ever change. They are like the material's stress DNA. It's the absolute unchangeable truth of its internal state, no matter your perspective. So what do they actually mean? Well, the first invariant, I1, that one's the most straightforward. It basically tells us if the material is expanding or contracting overall, like it's being squeezed by water pressure. I2 and I3 are a bit more complex. They capture the intricate dance between all the forces and measure the total intensity of the stress. But together, they give us a complete picture that's totally independent of our viewing angle. All right, that was a good bit of theory. Now for the big payoff. How do we use all of this to actually do what we set out to do? Predict when and how a material is going to fail. It's time to connect all this math to physical reality. To predict failure, it turns out we have to really focus on shear stress. But why? I mean, normal stress pulls atoms apart. That's obviously important. But for most metals, the failure process begins when whole planes of atoms start to slide past one another. And that sliding motion, that's caused by shear stress. It's what leads to permanent bending and yielding. Shear is the real trigger for deformation. And this slide illustrates the two types of stress perfectly. On the left, you've got hydrostatic stress. Think of it like deep-sea pressure, squeezing an object from all sides. It changes its volume, sure, but it usually doesn't cause it to break. But on the right, you have deviatoric stress. This is the part of the stress that actually distorts the shape. This is the real troublemaker, the one that causes angles to change and atoms to slide. This is the stress that truly leads to failure. Okay, we have all the pieces of the puzzle now. We know how to find the most important stresses, the principal stresses, and we know that shear stress is the main culprit for failure. So what does the actual map, the boundary between safety and failure, what does it look like? How can we possibly visualize it? This is it. This is the grand finale of our entire analysis. 3D Moore circle. Those three principal stresses we calculated, they define the size of these three circles. And that shaded area, that is the realm of possibility. It represents every single possible combination of normal and shear stress that can exist on any plane passing through that point. Any stress state inside this region is physically possible. But, and this is the crucial part, you can never have a stress state that exists outside the largest circle. That line is the absolute boundary of physical reality for that material. So, let's just take a breath and recap our journey. What we've put together here is so much more than just theory. It's a powerful, practical toolkit that engineers use every day to ensure things don't break. We really did this in 4 logical steps. First, we mapped all the chaos using the stress tensor. Second, we understood the critical balancing act of internal forces needed for anything to be stable. Third, we found that state of purity by calculating the principal stresses, where all the messy shear stuff disappears. And finally, we defined the absolute boundaries of reality with Moore's circle, giving us a crystal clear visual limit for safety. And this quote just says it all, doesn't it? We started this journey with an abstract mathematical idea, the tensor, and we step-by-step transformed it into a concrete physical understanding of safety. It really is the ultimate tool for making sure the structures we all rely on every single day are safe. So I'll leave you with this final thought. Just take a look around you, at the room you're in, the device you're watching this on. What invisible forces, what incredibly complex stress states are being perfectly and silently balanced right this second, all to keep your world from falling apart?